Hello students, welcome to the EN 401 lecture on vectors and static equilibrium. This is Lieutenant Dan Puckett. I'll be taking you through this. Alright, so here's the roadmap to this lecture. We're going to talk about Newton's laws of motion and how those help us derive some engineering mechanics, vectors and moments. Then we're going to talk about how we achieve a static equilibrium. Then we'll talk about free body diagrams and two force members, and then we'll have some practice problems. All right, so Newton's laws of motion. Hopefully you're familiar with these, from your many years in school. So I'm not going to, read these out for you. You can take a look at those. But from Newton's three laws of motion, we can, as engineers, come up with these study of mechanics, right? So the three main studies of mechanics are kinematics, that's the study of geometry of motion; dynamics, the study of forces and moments causing motion. And so those are usually build off of this first basic study, which we have bold here at the bottom. That is statics, and that's the study of objects at rest, right? So what does rest mean? So rest means not moving relative to some other object, right? So if we're studying things at rest on the Earth, that means, this thing is, whatever the object is not moving relative to the Earth, right? So, if you're standing in place and you're not moving, you're not running or anything, you're just standing there, right? You're at rest, you're not moving relative to the Earth. Although the Earth is, spinning around its own axis and spinning around the sun, and then that whole thing is, flying through the solar system and the universe, right? It's moving, but you're not moving relative to the Earth, so therefore you're at rest, right? So that's what that little star essentially means, right? So you could essentially be like in a car that's moving, right? But as long as you're not moving in the car, then you would be at rest. The car could be moving, but if you're studying your condition relative to the car, then you would be at rest. So the other piece of statics is we're going to assume that objects are rigid, right? That means if we apply forces or moments to them, that they're not going to bend or deform, and unaccelerated, right? So unaccelerated, we can kind of tie that back into our second law of Newton's motions here, right? So basically, Newton's second law says F equals ma, right? So if a equals 0, if the acceleration equals to 0, then the sum of forces on our system must also equal 0, right? So it doesn't necessarily mean that there's no force acting on it. It just means that to be in static equilibrium, to not be accelerating, that the sum of all the forces have to equal 0. And that sort of ties into the third law that says for every action there is an equal but opposite reaction, right? So a great example is, your own body weight, right? Your body has some mass that's acted upon by gravity, and gravity is pulling you towards the Earth, right? With some magnitude. And so if the Earth wasn't pushing back with the same force that your body is applying to it, you would sink down into the Earth, right? So if you're standing on solid ground, those the sum of your force of your body weight and the Earth pushing back against you, those are going to equal to 0. Whereas let's say you try to walk on water, the water can't resist your weight as good, and if you're really dense, you might just sink to the bottom. So some examples there. So why do we study statics? So as engineers, we build lots of things that have no relative motion, right? That are important in our daily lives. Great examples are buildings, right? Buildings are all engineered. They're not moving, so that's a great example of the application of statics. But some other things, roads, any type of utility system, pipes, power lines, all those kinds of great things that we do as civil engineers or ocean engineers. A lot of those things are at static equilibrium. They're at rest. All right, so how do we get this study of statics going? Well, we need to define what scalars and vectors are. All right, so a scalar is a quantity fully specified by a number, and it's going to have some type of scale with it. So good examples of scalars are mass, length, time, or temperature. Right? We want to know how much is in something, but that thing doesn't necessarily have some type of direction to it, right? So mass, tells you how much matter is in an object, but there's no real direction, associated with the mass of something. A vector, on the other hand, is we're going to have a quantity that's specified by both a magnitude and direction, such as force, velocity, or acceleration. So velocity, I think that's a pretty easy example, right? If you're in your car and you're driving at 50 miles an hour, you're going to be going in some direction. Maybe you're going 50 miles per hour, due east, right? So you have a velocity, you have a speed and a direction. So for statics, we're going to be doing a lot of studies of forces, right? So we're going to have a lot of magnitudes and directions with our forces, right? So we've got an example drawn here of a force vector. So we have this force vector R here, and it has a magnitude. And the magnitude would be the length of the vector, right? And then our direction would be this angle theta off of this horizontal x-axis. So forces are the main vectors we'll see in this class, and they have a magnitude, right? And the magnitude is equal to the length of the vector, and the direction is this angle theta. All right, so the great thing about vectors is we can resolve vectors into x and y components, and that's going to be really helpful when we start getting into our static equilibrium analysis. So it's a pretty simple process. So let's say we have this vector f here. All right, this vector f has this length, right? And this direction theta. So if we wanted to find the x component of that vector, we could multiply the f vector times the cosine of that angle theta. All right, and the reason we're using cosine to find the length of our, or the magnitude of our x component of our f vector, is because we're using trigonometry here. So trigonometry says if we have the adjacent side, then we're going to use cosine. Similarly, we can also find the magnitude of our y vector, our y component of our f vector, and that's just going to be this equation right here for this particular example, is the y component is equal to the magnitude of the f vector times the sine of angle theta, right? Because that goes along with the opposite side, right? Sine is for the opposite side. Right, so that's how we convert vectors into their x and y components. We just use a little bit of trigonometry, all right? And that will tell us the x and y components. So once we convert things into x and y components, we can do some analysis on them. We can add them together more simply. But we could also add, vectors like we have over here together. So f1 and f2. So let's say we wanted to add f1 and f2 together. We would just have to find the x and y components of both of those, right? We can add the x components together, right, from f1 and f2, and we could do that with 3 or 4 or 5 different vectors. We can just add up their x components if there were multiple, and then we can add up their y components, right? So we'll have the magnitude of the x and y components of those vectors, and once we have the magnitude of the x and y components, we can find the magnitude of the entire vector, right? And the magnitude is going to equal to the absolute value, the absolute value of the magnitude is going to equal to the square root of the x component squared plus the y component squared, right? So again, just some trigonometry that would give you the absolute value of the magnitude of the overall vector, right? If you added up the squares, or the square root of the squares of the x and y components. And then to find the direction of that new vector, you would just take the inverse tangent of the y component over the x component, right? So with all these things, we can use, and we start to get into our static equilibrium analysis. All right, so here's a bit of an example problem, right? We've got two vectors, f1 and f2, and this problem here wants us to resolve it into the x and y components for each. All right, so looking at our given information, we're given that F1 is equal to 4 pounds at 45 degrees, and F2 is equal to 6 pounds at 40 degrees. We're trying to find the x and y components of these vectors. All right, so how are we going to do this? So we'll just use the relationships we saw on the last slide, right? So in this particular case, theta is here. So that means our x component is going to be the adjacent side, and our y component will be the opposite side. So that means we're going to use cosine for x and sine for y. So we got that picture here for our f1. This bottom blue line here is our x component, and this is our y component of that vector. So we could use our trigonometric relationships to find the x and y component values. We can also label those before we do that. So we have f1x and f1y. And then we can go through and do that math. So f1x is our 4 pounds, which is our magnitude, times cosine of 45, and that's going to give you 2.8 pounds is the force in the x direction. And then sine and cosine of 45 degrees are the same value, so our F1y is going to be that same 2.8 pounds, right? So there are the x and y components of the F1 vector. So looking at F2, right? So F2, similarly, we have an x component and a y component. With our angle theta being 40 degrees and adjacent to the x side. So we can say that F2x is going to be equal to 6 pounds times cosine 40. And then F2y is going to be negative 6 pounds times sine of 40. And why are we negative? Well, because we are going, this vector is going down, right? This F2y vector is going down, so it's either negative 6 pounds, or this could also be negative 40 degrees there. So our F2x is going to be 4.6 pounds, and our F2y is going to be negative 3.9 pounds because it's going down. So that's the big thing with vectors, is to have a sign convention. Typically we deal with our sign convention will say that things that are positive are going up, right? So positive in the y direction is up, and positive in the x direction is typically to the right. So both of our vectors are going to the right, but F1 is going up, and therefore both x and y components are positive, whereas our F2 vector is going to the right, so we get positive in the x, but it's going down, so negative in the y. All right, so one of the more difficult concepts to understand with vectors and statics is the concept of moments, right? So I think a force is a pretty easy thing to conceptualize, right? We use forces all the time. We use a force to, move things and open doors and walk around, right? But the concept of moments is a little more difficult. right? Because a moment is a force that's acting essentially over a distance, right? And typically we have what's called a couple of forces that cause an object to rotate in space. So we've got this box here. This box is our object, right? And then we've got two forces. We've got a couple of forces right there, and one is going up on the right side, and one's going down on the left side. And those couple of forces are going to cause that object to rotate in space. So those forces are acting at a distance away from each other, right? They're both equal in magnitude, opposite in direction, and a lot of times we talk about moments, having a lever arm, right? It's a typical kind of way to talk about moments is there's a force acting over a lever arm. So the magnitude of a moment is going to equal a force times a distance. So the moment equals a force times a distance. So units that we're going to typically see with moments is feet times pounds or newtons times meters. And a lot of times we just denote moments with this arrow here with some magnitude and some units, right? So in this particular case, we've drawn a moment that is acting counterclockwise, and its magnitude is 100 foot-pounds. Right, so a moment is essentially just a couple of forces that are causing things to rotate into space. All right, so we have a little moment example here. So we have a TV on a shelf, right? So just a conceptual question, left or right, which method of putting the TV on the shelf is more likely to cause the shelf to fail, right? Is it more likely to fail in this first condition here on the left, or is it more likely to fail on this second condition here on the right? And I think conventional wisdom here just tells you that we want to mount it under condition 1, right? Just looking at it, condition 2 looks a little frightening. So we would want to put that TV all the way back against the wall. And mathematically, the reason we do that is because in condition 1, the TV is creating a smaller moment than in condition 2, right? Because in condition 1, we have this short distance here, right? So our moment would just be W times D1. That's acting on the wall here. Whereas in the second condition, we have W times D2, and D2 is much greater than D1. So our moment at the wall here at point P and the second state would be much higher, right? So it's going to be much more likely to lead to this shelf to failing. All right, so we got a couple videos here. So go ahead and pause this video and go into the slides and open up this moment video and open up this cheater bar video to get some more examples of what a moment is and sort of how they work. All right, so now that we've covered forces, vectors, and moments, we're going to move on to static equilibrium. So remember, static equilibrium is the study of objects at rest. So in this class, we're going to be covering two-dimensional objects at rest, right? And so how do we know if something is in two-dimensional static equilibrium? Well, we're going to say that it cannot be accelerating left or right in the x direction. It can't be accelerating up or down in the y direction. And it cannot be rotating or accelerating rotationally about the z-axis. So we'll see what that looks like in a couple slides with some examples. But for our 2D static equilibrium problems that we'll be seeing in this class, it can't be accelerating in the x direction, in the y direction, and it can't be accelerating rotationally. So it can't be, you know, spinning around like this. So how do we check for these conditions of static equilibrium? Well, we have three equations that we have to build to check for the conditions of static equilibrium being met. So the first condition is the sum of forces in the x direction is equal to 0, right? Because we said F equals ma, so if acceleration is equal to 0, that means the sum of forces in that direction is also equal to 0, right? And that would tell us that our object is not moving. So our first equation is this one right here, sum of forces in the x direction equal to 0. All right, our second condition of static equilibrium is no acceleration up or down, and so how we do that is we check to make sure that the sum of forces in the y direction is also equal to 0. So we'll build this second equation there. Sum forces in the y direction also equal to 0. And then our third condition for static equilibrium is to make sure that we're not experiencing any type of rotational acceleration about the z-axis. Right, so our z-axis is the one that sticks, you know, out of the computer screen. So we want to make sure it's not rotating like the circles I've drawn above. We want to make sure it's not rotating about that z-axis. So what we're going to say is the sum of moments about any arbitrary point in the system must also equal to 0. So that's this third equation here. So remember, a moment is a force times a distance, right? And so the distance is the distance away from the forces that are, the distance, it's the distance away from the arbitrary point to where the forces are in the system, right? So we have to have an arbitrary point so we can get a distance. If we don't use the same, you know, arbitrary reference point, then we'll have some distances that you know, they don't doesn't necessarily make sense. So we'll see how that works out in some example problems. So for our 2D static equilibrium problems, we can have up to 3 unknowns. All right, and why is there 3 unknowns? Well, because there are only 3 conditions of static equilibrium, so 3 equations. So we should know from algebra that with 3 equations, we can solve for a maximum of 3 unknowns. So you might be presented with problems that have 3 unknowns, or 2 unknowns, or 1 unknown. So the number of static equilibrium equations you need really depends on the number of unknowns in the problem. So if we have 3 unknowns in the problem, then we'll need essentially all 3 equations. If there's only 2 unknowns, then there are only 2 equations, and then just 1 unknown, just 1 equation. So how do we come up with these equations? Well, we're going to have to analyze the free body diagram. I've got that in bold there. So you analyze the free body diagram to determine the number of unknowns, and then we're going to do an analysis of all the forces in that system to determine whether it's in static equilibrium or not, or what the conditions of static equilibrium are, right? What are the forces required to put this system in static equilibrium? So we analyze the free body diagram. So now you're going to ask, well, what's a free body diagram? So a free body diagram essentially is a sketch of a body detached from the other bodies around it, right? So essentially what you do is you sketch out the system separate from everything else. So, you know, you might make what we like to call cuts in the system. We'll see that in the next slide, what that cut means. So you make a cut in the system, and then you analyze the forces in that system to make sure it's in static equilibrium. So important on our free body diagram, they need to indicate all the external forces, both known and unknown, and any moments that might be acting on the system. Right, so if we have some known forces, we need to make sure that those are on there. And then if we have unknown forces, we need to make sure that those are also listed on there with some type of label so that we can solve for them. So in bold here, it says the direction of unknown forces is arbitrary. The math will tell you if the direction is correct. So we'll go through and do our static equilibrium analysis with the some arbitrary direction on our unknowns. And if those prove to be positive, that means we picked the right direction. If we get a negative value for our unknown forces, that means we just picked the wrong direction, and actually the force is going 180 degrees the other way. So if we, decided that our unknown is going that way, but then it turns out that was negative, it really just means that our unknown force is going that way instead. All right, so any unknown force or moment should be labeled, right, with the appropriate letters, right? So if you have a force going in the x direction, you might want to call that fx. If you have a force going in the y direction, fy. If it's at a certain point, we might just use the name of the point. So that point, we might call it point A, or like the fulcrum. So we could have, an ax or ay. And again, that assumed direction for the unknown is not the most important thing, because if you get a positive number, that means, hey, you picked the arbitrary direction correctly. If you get a negative number, that just means the force is going the other way. All right, so once you get a free body diagram that has everything labeled, all your knowns and unknowns, then you can solve, so long as you don't have any more than 3 unknowns for two-dimensional problems. So if you have more than 3 unknowns, you may have done something wrong, so go back and take a look. But you should only have 3 unknowns for our 2D statics problems. All right, so here's a little photo example here. We've got the U.S. versus Canada in a little tug-of-war match, and they had this rope connected between the two of them. And let's say we want to do a static equilibrium analysis of these two guys. They're sort of in a standstill here, and we want to see what kind of forces are acting in the tug-of-war rope that's connecting them. So what we're going to do is we're going to make a cut. So this red circle here indicates where we're going to make that cut. So we're going to make a cut on either side of where those two straps are connected in the middle. And that will give us a free body diagram of the cable there. So that black dot indicates the connection. And then we have the force from the Canadian military member pulling to the left, and the force from the U.S. service member pulling to the right. And so there's our free body diagram. And what can we say about, if they're not moving, if they're in static equilibrium, what can we say about these two forces? Well, we know that the acceleration is equal to 0, so it means the net forces are equal to 0. So that means currently F of our Canadian service member is equal to the force of our U.S. service member. Let me erase this line here. All right, these two forces are equal. Right, so this would be some forces in the x direction equal to 0. So the force from our Canadian service member must be equal to the force of our U.S. service member. Once one person starts pulling harder than the other, so let's say FUS, becomes higher than F Canada, we'll see some acceleration to the right. And then, of course, our U.S. service member is going to win this tug-of-war match. All right, so the last piece for our static equilibrium analysis is two-force members. Right, so a two-force member is essentially an object that has only 2 forces acting on it. And we had a great example in the last slide with our service members. They were doing a tug-of-war match, and so our two-force member in that were the cable or the rope that was holding those two service members together. Right, there was one service member pulling to the left, one pulling to the right, and so those are your 2 forces acting in that member. So big things in two-force members. The forces, so it's in static equilibrium, so the forces must be equal, opposite, and they also must be collinear, so on the same plane. So our typical examples that we'll see of two force members are cables and tension and short column. So cables and tension, you know, this crane is a good picture of that, right? So this crane is lifting this reinforced concrete beam, and so we got our cables here. So if we were to make a cut in our cables there, we'll just look at one cable, not both cables. So we got our cable here. So we got the weight of our beam, of that concrete beam pushing down. Erase these erroneous lines here. So we got the weight of our concrete beam pushing down, being pulled down by Earth. But then we also have the force of the crane pulling up on that beam, right? So that's our two force member, our cable. We have a force down from the weight of the beam, and then a force up from the crane pulling that beam up. And then we also have short column. So, you know, taking a look over here at Stonehenge, right? So if we were to look at just one column here, let's just take a look at this one column there. And we have this weight of this this rock right here on the top, right? So we'll draw this over here. So we got that big rock on the top there, and that's pushing down on our rock column. And so in order to keep that thing from falling down, the rock column is pushing up. So that's our two force member in compression. Those forces are in the same plane, right? If there is some distance between those two forces, we get an internal moment there, and our two force members they can't take internal moments, right? So in our two force members, those forces that we'll be analyzing are in the same plane, and they are going to be equal and opposite in collinear. So there won't be any deviation off of the plane that they're acting on. So an application of two force members in statics are the simple machines called pulleys. So pulleys are simple machines that can be analyzed using static equilibrium analysis. Some assumptions in pulleys. We're going to say that so the tension in any pulley cable is going to be constant across the cable. So in this picture we have here to the right, the professor is pulling on this cable, which runs over this pulley and then it's connected to this box here. So the tension in this cable is constant throughout. So this is a two force member. So the tension is constant throughout that cable. And then the pulley itself here, we're going to assume it's frictionless. So these are sort of ideal conditions, so we can do our static equilibrium analysis. If there was friction in this cable, that could change the tension on the effort side versus the load side. So we're going to say it's frictionless, so that these are the same. So the way we analyze pulley systems is using a free body diagram and static equilibrium analysis. All right, so we've stopped our professor here from actually lifting up this wooden box here, and we're going to apply some numbers and ask some questions about this box. So question 1 here, so if the wooden crate has a weight of 135 pounds and the professor is pulling at an angle of 30 degrees from vertical, how much force is he pulling with? All right, so we got our crate here, downward force of 135 pounds, right? So if we just did a little free body diagram of this area here, we would see that to get this in static equilibrium, we would need a force up of 135 pounds. All right, so what does that mean? That means the tension in the cable on this load side is 135 pounds. So what is the tension on the effort side? Well, the tension in the cable is going to be constant. So the tension on the effort side is also 135 pounds. which in this case means the professor has to pull with 135 pounds to keep this box in static equilibrium, just barely off the ground. Right, so we have 135 pounds in tension anywhere in this cable. So question number 2, how much force is the pulley resisting in the X and Y directions? All right, so how are we going to analyze that? Well, we need to do a free body diagram around this pulley. So we've got 135 pounds down here. We've got 135 pounds at this angle here. Which was 30 degrees. All right, this angle is 30 degrees. And the pulley is not moving, right? So our pulley is going to be resisting a Y component and an X component. So you can go ahead and solve that. The answers are in the notes on the PowerPoint slides. So go ahead and solve that, and you can get those answers there. And then once you have those answers, find the resultant force that the pulley is resisting, right? So we'll have to find the resultant force of those two forces, that X and Y force. So you should get some resultant force with some magnitude and a direction, right? So find that force, magnitude, and direction. And again, those answers are in the speaker notes. All right, so there's a couple example problems, videos that will be posted. So make sure you watch those for this lecture. They'll really help with the understanding of the material. But here's your review. So make sure you know what a scalar is and the difference between a scalar and a vector. And then you really need to know how to resolve vectors into their X and Y components. Remember, we just used trigonometry, SOHCAHTOA. Sine is for the opposite side, cosine is for the adjacent side. So sine isn't always for Y and cosine isn't always for X. You just have to take a look at the free body diagram and determine which side is the adjacent, which is the opposite, and then use the right trigonometric function, so cosine or sine, depending on adjacent or opposite side, right? So that adjacent side again is for the cosine, and our opposite side is for the sine. All right, so you should definitely know when static equilibrium is achieved. All right, how do we achieve static equilibrium? We have to make sure it's not accelerating left or right or in the X direction. We need to make sure it's not accelerating up or down or in the Y direction, and we need to make sure that it's not rotating about the Z-axis, right? So the Z-axis is the one that comes out of the page, out of the screen right at you, so that would be rotation around the Z-axis. We need to make sure this thing is not rotating in space. So to achieve those three conditions, we need to have three equations, right? So some force is X, some force is Y, and some moments about point A, all equal to 0, right? The purpose of the free body diagram, you should know that. We need the free body diagram so that we can analyze the forces and the moments acting on the system, and then use those to build our static equilibrium equations and to check for any type of acceleration. And then again, be sure to watch all the example videos. I highly recommend taking a look at the examples in the slides, not looking at the solutions and trying to work your way through them. And then watch the example video to see how well you did. So, all right, I hope you enjoyed the lecture. If you have any questions, be sure to reach out to your instructor.